Hi everybody, it's Mr. Poser, your AP Biology teacher. Today we're getting into topic 3.3 on cellular energy. The name of the unit is cellular energetics, and thus this topic is going to cover a lot of the main points and the kind of overviews of metabolism and reactions and energy transfer and all that kind of stuff. So we're going to take a step back here from the really specific stuff because we're about to get into that in topics 3.4 and 3.5, which are on photosynthesis and cellular respiration. We got to get an overview of some of those processes here a little bit, or the background behind those processes before we get into the nitty-gritty details and the specifics of some of those mega important processes that happen in living things. All right, so throughout this kind of series of videos here, a couple things that we've talked about are like, okay, all living things need to be able to do X, Y, Z. And this list is not comprehensive. It doesn't cover everything, but it does kind of talk about the requirements of living things that we've discussed so far. So here we go. Living things are highly ordered systems that must 1, take in nutrients and get rid of waste. All right, we talked about that. Unit 1, a little bit. Unit 2. Number 2 was all about cells, or Unit 2 is all about cells. So number 2 is be made of cells. So, all living things have to be made of cells. 3, they have to maintain a stable internal environment. All right, so what we talked about with the plasma membrane has to control what comes in and what goes out, separates the internal environment from the external environment. And that is tying back to our last topic on enzymes and environmental impact. It needs to make sure we got this right temperature, we got the right pH, etc., for enzymatic reactions. But we haven't gotten into quite a bit about energy just yet. And another requirement for all living things for us to do is to obtain more energy than we use. Okay, we have to obtain more energy than we use. This feels maybe a little complicated when you say it, but I'm going to come back to that because that's a really big idea here. And this whole thing is about cellular energetics. So before we get into like, all right, how do living things obtain more energy than they use? How does that happen? We got to talk about the ground rules here. And by the ground rules, I mean the laws of thermodynamics. All right. Now, we don't have to get too much into the physics here, the physical science, etc. Maybe you took a class where you studied the laws of thermodynamics already, so maybe you know this pretty well. Maybe you don't. I'm going to go over the gist of it and how living things are related to these here. All right, so the first law of thermodynamics, you guys, is that energy is conserved. It means it cannot be created and it cannot be destroyed. Okay, so living things don't break the first law of thermodynamics. What we're able to do is transform one form of energy into another. All right, namely, like, for example, photosynthesis is our next topic. That's taking light energy and transforming it into energy in bonds between atoms to form new molecules. So taking light energy, electromagnetic radiation, and converting it into a chemical bond, which is kind of amazing. So living things are able to do that. We're not able to create energy. We're not able to destroy energy, and energy is conserved. That's the first law of thermodynamics. Now, the second law of thermodynamics states that every time energy is used, it increases the disorder, or what's called the entropy of a system. It means things kind of, energy dissipates and things go from a higher ordered state to a lower ordered state and becomes kind of more messy and jumbled up. Entropy is a pretty poorly understood concept across all disciplines here, and we don't have to get into the specifics about entropy for right now. Hey, but the gist of it here, as it applies to biology here, is that these energy transformations that living things have to do, all right, in order to stay alive, are not 100% efficient, and in fact, no energy transformation is 100% efficient. Photosynthesis, respiration, doesn't matter. Well, any type of chemical reaction, because that's really what life is, right? Just a complicated array of chemical reactions. None of them are 100% efficient, and energy will be lost, always. Energy will be lost as heat. And that lost heat to the environment, or whatever, that's whatever energy is not being used or just, kind of wasted, that increases the entropy of a system. All right, so these are the two big things over here. Number one, we use energy transformations, okay, to power cellular processes, and those energy transformations are not efficient. All right, so we are losing energy all the time. We're using energy for, any type of cellular process, but we're also losing it to the environment. All right, so that illustrates here that we're using and losing energy all the time, and therefore our input must be greater at all times than our output. Because what do you think happens if your output is greater than your input? Well, you die. Okay, you're going to run out of energy eventually, and once you run out of energy, you are not going to be able to have any cellular processes, and that's the end. That's it, So as I put up here, living things' energy input must be greater than its output. Loss of energy flow results in death. Okay, all of our energy is borrowed, right? Energy gets transferred from one to the other. We can't create our own energy. We can't destroy our own energy. So we get it, intake it, and then output it. And the intake always has to be greater than the output. All right, all of our energy is just borrowed, right? Energy transformation should be efficient to decrease excess energy loss. Okay, so energy loss is inevitable, right? We follow the second law of thermodynamics. Not all these energy transformations are going to be 100% efficient. And either way, okay, whatever we do, we have to decrease the output and increase the input, right? To make sure that the input is greater than the output, what living things do, okay, or what just happens in living things is that there's a couple measures that are taken to make sure that all these energy transformations and these reactions are efficient. And we're going to talk about two ways that they're tried to be efficient here. Okay, but before I get into that, this is a kind of highly oversimplified map of what's called metabolism, right? I talked about metabolism being the all the reactions that happen within a living thing, right? And you can make a map of reactions. How can you make a map of reactions? Well, it depends on what are called metabolic pathways, which is what I'm about to introduce to you here. This is stylized as like a metro map, like bus lines and like train lines and that kind of stuff. So I think that's pretty cool. But the point stands here is that all these lines on here are all what are called metabolic pathways, which are sequences of reactions. All right, and reactions happen in sequences in living things because it conserves energy in a way. All right, it reduces the amounts of energy that's released into the environment, and living things try to be efficient with our reactions here. So one of the ways living things save energy is through metabolic pathways. And basically, the gist of a metabolic pathway is that the product of one reaction becomes the reactant of another pathway. So things happen sequentially. Mega simple right here. Ready? I have compound A, some kind of substance, whatever it is. If I'm a living thing and I gotta transfer that or transform that into something else, all right, I'm gonna use an enzyme and I'm gonna transform it into compound B. Great. But then compound B can be used with another enzyme to mediate that reaction. Compound B can be converted into compound C. So check it out. B, which is the product of one reaction, becomes the reactant of another. And this can go on and on and on and on and on and on and on in a very, very complicated array. So here's my pathway again. Which are enzyme mediated, another way that living things can be more efficient with their energy is with pairing reactions that release energy to the environment with reactions that take in energy from the environment. Those two terms are endergonic and exergonic, but I won't necessarily have to get into all the specifics here. But as I put, a reaction or process in a pathway that releases energy may be paired with one that requires energy in order to reduce the energy lost, right? So any energy that comes out of one reaction can be used by another in order to try and maintain as much efficiency as possible, right? Why waste that energy that's being dissipated out into the environment when it can be used for a subsequent reaction? So metabolic pathways are often, kind of oriented this way, all right, where not only does A become B and B becomes C, things happen sequentially. Reactions are often what are called coupled. This is called energy coupling, where one that releases energy is paired with another one that takes in energy, so the energy released from one can be used to power another. All right, that's called energy coupling. And this is another way that metabolism and living things try to conserve energy and make sure that the output doesn't ever become greater than the input. Okay, last point I want to make here is that certain metabolic pathways, some of which that was on that big map that I showed you, I don't want to flip all the way back, like a few that we're going to talk about as well in topic 3.5, like glycolysis and oxidative phosphorylation. You can find them among all types of living things. All right, between all three domains, there's archaea, which are ancient prokaryotes, bacteria, which are prokaryotes, and eukarya, which are, eukaryotes, your protists, animals, plants, fungi, that kind of stuff. You can find some processes among all living things. And does that suggest common ancestry, that all life originated from, a common ancestor? Yes, it does. All right, but save that topic a little bit more for Unit 7 because That's all about evolution and common ancestry and stuff. But just so you know, okay, not only is that energy coupling and the metabolic pathways, one reaction happening sequentially after another, not only is that conserved among all living things, but certain metabolic pathways like A becoming B, becoming C, becoming D in the same way are also conserved. So here you go. Here's the recap in case you missed anything. In case you missed anything or I missed anything, life requires a greater input of energy than output. Life doesn't violate the first and second laws of thermodynamics, all right? Input has to be greater than output because energy is transformed from one form to another, but it's not 100% efficiently. So energy is used, but it's also lost, all right? So we got to make sure our output is lower than our input. Reactions happening metabolic pathways where products become reactants in other reactions. Energy from one reaction is used to power another one. All right. Metabolic pathways are conserved among all living things. You can find ones like glycolysis and oxidative phosphorylation among all types of cells. Okay. So living things have to be efficient with our energy. We use metabolic pathways and we use energy coupling for that. We got to make sure our output is lower than our input. And some metabolic pathways are all conserved. You can find them among all different types of life. All right. That is it for topic 3.3. We're getting into one of the big ones, 3.4, in our next video. So stay tuned. Let me know if you have any questions, and we'll see you next time.